Alright, so section 2.2 is about describing sets. And the first thing we're going to take a look at is a little bit of vocabulary so that we're all using the same vocabulary when we're talking about things. The first thing is flat out to decide what a set is. Because it says describing sets, well, what do we mean by set? A set is simply any collection of objects. So it's what you mean when you say my set of books, my set of friends, my set of family members. It can be talking about any collection of anything, okay? And then an element is simply an object in that set. So whatever your set is, it's the things that you're describing in that set. So if we talk about the set of people in my family, your mom's probably included in there, and if your brother or a sister, okay? So those are different people in your set. Those would be the elements of your set. If we're talking about your collection or your set of books, well, then each individual book would be an element in that set. When we describe sets, there's several ways to do that. One way is simply to list everything out. So if you describe the set of people in your family, you could say, or I would say, in my immediate family, I've got my husband, my daughter, my son, and then my daughter is in Ethiopia. So I could actually write them out. Like just list all their names or list the description of who they are. And we do that, we put that in curly braces, which we'll do in a minute. The other one is set builder method, and that's the one that looks a little bit more mathematical. It's got the curly braces like the other one does too, but it describes things using variables usually. Okay, so we see a little bit more mathematical notation in that set builder notation. Some common notations in set builder notation. So these you may or may not have been familiar with, and I'm going to be using them, so I want to be able to reference them so you've seen them before. So the first symbol that I'm going to talk about is it looks like sort of that curly E. It's an epsilon, Greek letter epsilon. This actually means is an element of. As in, my husband is an element of the set describing people in my family. Okay, so that E means it is an element of it. It's one of the items in that set. The rest of these are actually symbols for number systems. Okay, so if you had, okay, just a sec. You guys seen me do this before? Yeah? Okay. That was new though, wasn't it? Okay. So the rest of these are actually symbols for number sets. So do you remember what this one is? Those of you who have seen this one before? It is. It's the natural numbers. So this is the natural numbers. And sometimes the natural numbers are called the counting numbers. And these are the ones that when you very first start learning to count when you're a tiny little 2-year-old or whatever, 1-year-old, however it is you are, what's the first number you start when you're counting with? 1. We start with the number 1. So our counting numbers are our natural numbers. There's my curly brace. Are the numbers 1, 2, 3, and so forth. So stop for a moment and tell me what things do you not see in this list? 0, negatives, decimals, fractions, even weirder things like pies and square roots. They're not there either. Okay, so these are the counting numbers, the natural numbers. All right, the next set is the whole numbers. You see, we're going to do this sort of double lining thing on the left-hand side of almost all these letters. So these are my whole numbers. Do you remember what this one gets to include that the natural numbers didn't? 0. So when we first learn to count, and we're in first grade, up through about first grade, we have this idea that numbers are only these whole number things, 1, 2, 3, 4. And at some point somebody says, well, what happens if I have 5 minus 5? And all of a sudden you don't have a number that represents that, so you need an additional number, and that number is 0. And everything else stays the same. So all of those other numbers are also whole numbers. So they're in 2 categories, right, so far. They're in the natural number category and the whole number category. The whole number category includes one additional item, the 0. All right, next thing happens is that somebody says, great. This actually happened, my husband did this to my daughter, was so neat. He said, okay, well then what's 3 minus 5? She's like, say what? Right? Because 3 minus 5, you can't do that. In fact, I think that's probably what she said, is you can't take 3 minus 5. You can't. Not with these kinds of numbers, right? What do I need in order to do 3 minus 5? Negatives. And so there we go, the integers. So the integers have a symbol of z. It has to do with the Latin word for integers having a z. Okay, so that's where that z is coming from. It's not an I. And then we get to include all the negative whole numbers. So we're going to put that dot, dot, dot at the beginning, and I'm going to have -3, -2, -1. But I still have all the others as well, 0, 1, 2, 3. It's like my universe of what I think of as a number just keeps expanding. I'm just adding on to what I had before. Okay? So the number 2 is a whole number and a natural number and integer. It's in all three of them, and that's okay. But there are definitely some things down here in the integers that did not occur before, like -5. All right, and that's all well and good until about 3rd grade. I can't remember if she did it in 2nd or not. I know it happened in 3rd grade. And in 3rd grade, somebody said, okay, now you have 5 cookies and you have 3 friends. How many cookies does each friend get? Right? You could say, well, I'm just going to eat them all and they don't get any. That's not what we're trying to do here, right? What's the problem with 5 divided by 3? Get a fraction, don't I? So I need to expand my view of what numbers look like yet again. And I expand them to what are called the rational numbers. And the rational numbers are a Q. And all of a sudden, I don't have a way of writing them out with these curly braces. Okay? There's not a closed, simplified way to write them out. So what do I mean by them, though? Well, I mean that, so I'm going to describe them in words. So these are decimals, fractions, and they include all the numbers above as well. Because I can always take one of those numbers. Let's take the number 3. And I can write it as a fraction. How can I write 3 as a fraction? 3 over 1. So 3 over 1 as a fraction makes 3 a rational number. So all the numbers we did before are also called rational numbers. Any idea why they might use Q? That's what it is. Say it louder for me, Carrie. It's because of the word quotient. What does quotient mean? It means division. And what did we just say rational numbers were? Fractions, and fractions represent division. At least that's one of their meanings, right? So quotient actually comes from this idea of doing a division of something. In particular, it's a division of integers. That's what we're looking at. All right, but then we've got things coming up in later elementary school called right triangles. Do you remember those right triangles, those pesky little things? And you have this wonderful formula about right triangles. Do you remember it? Remember the name of it? The Pythagorean theorem, and Carrie's telling me it's a squared plus b squared equals c squared, right? And very quickly, when you start using the Pythagorean theorem and you start finding side links, what comes out of that? Square roots come about, don't they? And square roots don't have the ability to write it as a fraction over, or an integer over an integer in fractional form. They don't have that ability to do that. So we expand our universe a little bit larger in terms of what we consider to be a number and what we all end up calling real numbers. And that's really as big as you're going to be seeing until you hit high school. So that's as far as our book goes. So we've got real numbers. So the real numbers is everything above. All right, so just like before, we've got everything above. They're real numbers. But now we include things like square root 2 and square root 7 and so forth. We also include the other kinds of numbers that you see like pi, right? And you'll see pi when students start working with circumference and area of circles. Okay? That's 4th to 5th grade. So it's pretty young. It's younger than you probably remember doing it because there's been a lot of curriculum changes since you've been there. Okay? So these are the number systems. I want you to know what these symbols mean because when I use them, I don't want you to be looking at it going, what was that again? Okay, so reference this if you need to because we're about to use some of these. All right, so example number 1. It says we're going to write the set of all natural numbers less than 5 using these 2 methods. The first method is the listing or roster method. And then the second method is that set builder notation method, which we haven't actually done one in yet, but we'll get there. So the listing method means that I use curly braces, and I simply write out everything that this described. So what will I write inside of my curly braces? 1, 2, 3, and 4. I close my curly braces, and for this particular set, that was no problem, right? Just a few numbers, I can list them all, I can do it very quickly, it's very clean, right? Set builder notation is going to look like cumbersome. It's not going to look especially helpful for this, but it's going to look helpful in other situations, so we're going to take a look at it in this situation too. Okay, so set builder notation starts with a curly brace, and it starts with an X and a bar. Let me get it all written out, and then I'll describe to you what this is actually saying in terms of math talk, okay? The next thing it's going to tell you is that X is less than 5, because that's what it said. I actually have to do that symbol, X less than 5, but that's a symbol you guys know, so that's not a problem. But what we don't want is we don't want to include things that are not natural numbers, right? This says natural numbers, so we have to actually say, hey, I'm talking about natural numbers here. I don't want the negatives, and I don't want 0, and I don't want the number 1/2. I don't want any of that other stuff. So the way that we do that is we put that same X, we put that epsilon symbol, and then we're going to put the natural number symbol and close it off. This is the notation. Now let me talk you through what it actually is saying. This first X is saying all numbers X. This bar here is read as the phrase such that. That means with the following conditions, as long as the following things are happening to be true about it. Okay? Such that. Of course, you guys know what this one is. This says X is less than 5. And this phrase right here says X is an element of the natural numbers. Or for short, X is a natural number.
Couldn't you just say X is greater than 0?
You could, but it still wouldn't eliminate the numbers like 1/2.
Okay.
And so there's a problem with that, right? We still have to specify which one of them. And that would take care of part of the problem, but not all of it. Yes, Carrie?
Could you, like, flip X less than 5?
These two?
Yeah.
Yes, you could. That would be okay. Yeah. So anytime I'm clarifying one of these pieces, almost always there's two pieces in there. There's one piece that talks about the restriction of being less than or greater than certain things. And then there's another piece that talks about what kind of a number it is. Is it a natural number? Is it a real number? Is it a rational number? And you have to specify which number system you're working in. So there's almost always these two pieces that are going on inside there. And like Carrie said, if we switched them, that would actually apply too. Okay, so I have no problems agreeing with you that for this particular problem, why bother, right? This seems unnecessarily difficult. But that's not always the case. So let's try the next one. Hopefully I've got one in here. Oh, I don't have one. Let me change one and I'll give you another example so I can show you one where it is helpful. Let's say for a moment that instead of saying what it said before, it said X is a rational number. Less than 5. We'll still stick with the less than 5. The problem, so to speak, here is that I changed number systems, right? I changed from natural numbers into rational numbers. The reason that's a problem is because part A on this problem told me to write out a list. You are not able to list all of the rational numbers between 0 and 5. In fact, you wouldn't even be able to start at 0. You'd have to include all the negatives as well because rational numbers can be negative. This isn't possible. It's not a closed form. There's not a simple list of things I can include. But if you take a look back at this notation we created here, the notation for what we would want for this problem looks almost identical to this. I still have all X such that X is less than 5. The only difference is that instead of X being a natural number, we say X is a rational number. And I have a closed form way of describing that. It just doesn't look like a list of numbers. Does that make sense? So there are cases when this is the only option, or even a better option sometimes if there's two options. Okay? Let's say, for instance, I wanted the natural numbers from 1 to 100. Okay, I don't want to write them out 1 to 100. That's doable. I mean, I can do it, but it's not especially good use of my time, is it? I don't think so. But I could do a form like this, where I was kind of a closed form of writing it out. It's much more condensed and a much better use of my time and paper and ink than the other. All right, let's go on to something else. Equal sets. All right, two sets are considered to be equal if they have exactly the same elements. Okay? So if I were to describe my immediate family as a set and my husband were to describe his immediate family as a set, they'd be equal because we're talking about the exact same members of something, right? But that doesn't always happen when a husband and wife do that, does it? It doesn't, right? Because we have blended families and things don't always work out like that, right? I have a brother-in-law and he has a daughter from a first marriage, and if he and his wife described this, his wife describing her immediate family, if she talked about her biological immediate family, would not include his daughter from his previous marriage. It would be different sets, okay? So equal sets have to have exactly the same items in them, the same elements. A one-to-one correspondence is actually a way of pairing elements into sets so that there's a 1-to-1 ratio, okay? So imagine if you showed up at a party and there's 5 boys and 5 girls. In theory, we could do a one-to-one correspondence and everybody has a dance partner, right? Okay? But this is a problem if you show up and there's 7 young ladies and 4 young men. You can't all have a dance partner at the same time, right? If it's a boy-to-girl correspondence. So if you want to take a look at a picture form of this, you can talk about creating a set, for instance, that has 3 symbols in it, A, B, and C. So my set is the letters A, B, and C. And I can talk about a set over here, which is the numbers 1, 2, and 3. And because there's the same number of items in each set, it is possible in a variety of ways, but it is possible to create this one-to-one correspondence or pairings of the items. Okay? When you're able to do that, that is when the 2 sets have the same number of items, we call those sets equivalent sets, which is just terrible, terrible vocabulary. Would you agree? Equivalent, equal, we use those words interchangeably all the time. But in set theory, they mean something different. Equal means exactly the same elements. Equivalent actually means that you could have just the same number of elements. So my family, 5 people, right? My son and my daughter, they're here, my daughter in Ethiopia, and then my husband and I, 5 people, would be equivalent to my sister's family. She also has 3 children and a husband, they have 5 in their family. They are not equal sets, but they are equivalent sets because they have the same number of people or number of elements in them. Okay, so those mean different things. Okay, so we're going to talk about one-to-one correspondences now and how we figure out how many of them there are. Because you see, when I did this right here on this 4th slide right here, I sort of did this sort of funny, B to 3 and C to 2 thing going on, right? That was one way to do the correspondence, but I could have just drawn the line straight across, and that would have been a different correspondence. Does that make sense? All right, so we're going to do this same idea, but we're going to do it with 6 elements. So I'm going to draw the picture for what's going on first and explain what's happening, and then we're going to actually do the calculations so that we can see how to do it in a simplified form. Okay, sort of a problem-solving kind of thing. I'm going to do it with a simplified case, though, with the 3 elements like I talked about just a moment ago. Okay, so let's imagine that we have a set with 3 elements, A, B, and C. And I have the 3 numbers 1, 2, and 3. How many different numbers could A correspond to? 3. I could go from A to 1, or A to 2, or A to 3. So A has 3 possibilities. However, it only can go to one of them, and once it goes to one of them, and let's say for a moment that it goes to number 1, then the number 1 is out of the picture, right? So when your best friend gets married, you can no longer viably date her husband. He's out of the picture. He doesn't get included. So they show up at the party, they are a pair automatically. It doesn't matter how many people are there, they go together. Okay? Now, we've got B and 2 and C and 3. So B now has how many options that it could correspond to? It has 2, right? So B then has 2 options. And then the last one, of course, once B has been paired up with some number, and we'll just say the number is 2 so that I can keep my picture going a little bit more cleanly, then C has how many options? 1, right? They're like the last person picked for dodgeball. Right? Okay, so we've got this last pairing because they're the ones that are left over. And one of the, in fact, do I have it here? I don't remember if I have it in this section or not. Yeah, it's later in this section. One of the things that we're going to see corresponding here far, far down in this lesson is we've got something called the fundamental principle of counting. And it says that when we take a look at the number of ways something can happen, we would multiply all the different single options together. So if there are 3 ways that this could happen, and there are 2 ways that this could happen, and there's 1 way that this could happen, and we multiply all 3 of these together, I would have 6 different possible pairings that I could have written down. And if we actually wrote them all down, A1, A2, A3, and then I've got A1, B1, A1, B2, C3. There's 1 option. I could do all this, and I could actually pair these all together, and I would have 6 different options for how these compare. Okay. So what do you see happen? What did I get? I had 3 different elements in my set, right? A, B, C. And I have 3 times 2 times 1 ways that pairings could happen. So what do you think would happen? Try to generalize that. What's going to happen when I have 6 elements? It's not 12. Try to say it louder for me, Katie. You can do 6, 5, 4, 3, 2, 1. Right? 3 elements, I did 3, 2, 1. It's the same idea. So the way that I always think about drawing it is like this. I have 6 different original characters, 6 people, or 6 women, or 6 whatever you want to use. So if we do women, we have 6 women come into the room and there are 6 men there. Person number 1 gets to pick from among 6 people. But once she picks, she snags her guy and she heads out the door. Person number 2, female number 2, comes in. There are no longer 6 males in the room, there are now 5. So she only has 5 to pick from. And so forth all the way down. And then with that fundamental principle of counting, which we'll talk about a little bit later too, we know that we can multiply these together. Yes?
Okay, I'm kind of confused on why you multiply.
Well, let me take a look at that first example, and we'll actually write it out so that I don't have to write out 6 cases. And I'll do that here in just a second. Let's find this number. What do I get when I multiply 6, 5, 4, 3, 2, 1? What is it? 720. I think that's on 2. Yeah, that's what I have written down. Okay. All right, so let's go back up to the first one that we had where I did the simplified case, where I had A. So I could do A with 1, right? If I do A with 1, I could do B with 2 or C with 3. But I have another option. If I do A with 1, I could also do B with 3 and C with 2. And those are 2 ways that I could do A with the number 1. But I'm going to get 2 ways that I can do A with the number 2 as well, for the same reason. So if I did A with 2, I could do B1, C3, or I can do A with 2, and I could do B with 3, C with 1. And the same sort of picture would be one more time over if I did A with 3. So that's what's happening. And it's doing it 3 times 2 because there's 3 people originally. So here A has 3 choices, B has 2 choices. And so that sort of a pattern continues when we create more choices with more elements. Okay? Okay, good questions. All right, cardinal number. When we talk about the word cardinal number or the phrase cardinal number, all that really means is the number of items a set has. So if I have a set S and I denote it N with the parenthesis S, that means the number of items in set S. So if we talked about my family and we said N of Dr. Gann's family, it would be the number of people in Dr. Gann's family, and we would have 5. Okay? And that's it. That's all it means. And then if something is finite, it simply means that you know how many he is, right? So the number of members of my family is finite. Most of yours probably are. But you do know of someone who was told that his descendants would be infinite. Who was it? Abraham. Abraham Abraham, Adam by definition would have been too big. Abraham was actually told by God his descendants would be as numerous as stars in the sky and as the sand in the seashore and top. Right? It'd be infinite. Okay? So infinite simply means that there's not a whole number to describe that. Okay? And you have this idea of it being something that's very, very, very large. But you've all had this conversation probably when you were a child arguing with a brother or sister that says, I hate you more. Or I love you more. We'll go with that one. I love you more. I love you times 2. And I love you to infinity. And I love you infinity times 2. We can always talk about something bigger, right? This is the idea of infinity, something bigger. Okay? And then we have one more here that's called the empty or the null set. And it has a symbol. So this is a set that has nothing in it. And so I used to be able to say, in fact, as recently as last semester, I said, I can tell you all about the wonderful teenagers in my home. I can still say it at the moment because my teenager's not in my home yet. They're wonderful. They pick up their clothes, they do their dishes, they do everything that they're supposed to do. And it's easy for me to talk about them, and everything I say about them is true because there were no teenagers in my home. That's an empty set. We can talk about the gerbils in my home. We'll go with that one. I have no gerbils, okay? We'll talk about the gerbils in my home. They're so clean. Their cages never need to be cleaned. They're great. Fabulous pet. Because I don't have one. I don't have one. I don't think they're actually a fabulous pet. But, okay, so this is the null set. This is the idea of describing something that has nothing in it. Okay? So it has a symbol. The null set symbol looks like this. It's a 0 to slash through it. So don't ever use that 0 to slash through it and think you mean the number 0. It doesn't mean the number 0. It has a couple of meanings. One of the meanings is the empty or the null set. The other meaning is actually what? Do you remember it? You've seen these used before? When you get to algebra, sometimes you'll use this for the phrase no solution. Okay? It doesn't mean 0. So this symbol is not interchangeable with the number 0. However, I can talk about the number of items in the empty set being 0. Because when I put that in front of something, it means number of items. Okay? Let me do one more sort of description to clarify something here. If I talk about the set, the members of my family, this is actually a description of a written out description. I'm going to use that listing method of the members of my family. So I'm going to use their initials just because that way I don't have to write them all out. There's my husband, Jeff. And I should probably include myself in here, so we'll put me in first. There's myself. There's my husband. There's my daughter, Abby. My son, Eli. My other daughter. And so I have all of these letters. So this is actually the list of the people of my family. But if I were to put an N in front of this, and I put members of my family, no longer am I being asked to write out the members of my family. What am I being asked to do? The number of them. I'm asked to count them. So when I put that N in front of something, it's no longer asking me for a list of something. It's actually asking for the number of people that would be in that list. In this case, that'd be 5. That is a different notation. Once you put that in front of something, it's asking for the number of items inside of whatever you're describing. Okay, these are clear. That's okay. These are confused with each other often. Yes,
So how do you do it if it's infinite?
if it's infinite, you can't list them, and so you have to do a description, or you can use that set builder notation. All right, so we're not going to do Abraham's descendants, but if we were to do something with numbers, say for instance, and we talked about all natural numbers. One of the things you can do is you can do 1, 2, 3, 4, dot, dot, dot. That's one way to do it. Or you can describe it with that other notation, that builder notation where you put x such that x is a natural number, something like that.
So then what would the number of that be?
The number of that would be infinity.
Okay.
Yeah. So if you were to talk about the number of items in any of our number systems that I wrote earlier, flat out, this would be infinite. And it's that sort of sideways looking A symbol. The infinity symbol. Yeah. Okay, let's do cardinal numbers for a few of these. So there are 4 sets here, and we've worked with some of these kinds of ideas because we did it with the arithmetic and geometric sequences. Do you remember? Mr. Gauss as well, we talked about him. And you had to be able to count how many items things had in them. This is the same idea again, down to it one more time. So if we're trying to find the cardinal number of each set, that is, we're trying to find, we'll call this set A, B, C, and D, just so that I can talk about the notation one more time. If I want the number of items in set A, how many items are there in the set from 9 to 99? There are 90, 91. How do you decide? Do you remember?
Then you subtract
You're really close.
it's 9.
It's actually 8. Why?
Yeah, it's nice to include
Before. So the way I always think about it, Hannah, is that I take the numbers and I pretend like I actually started at 1. If I went from 1 to 99, how many numbers do I have? 99 of them. But I actually am missing the first portion of them. I'm missing the first 8. So I'm subtracting actually 8 because those 8 are not there. So this is actually the number 91 on this one. Okay? I'm missing the first 8. How about on the second one? What kind of numbers are you seeing? They're evens. So again, if I were to start with the first number being 1 and go all the way to the number 2002, I would have how many numbers? 2002, but I don't have all of them. I only have the evens. So what do I have to do? Divide by 2. So if I'm talking about the number of items in set B, I'll write that down. It's actually 2002 divided by 2. So how many numbers do I have? 2001, right? Okay, C and D are a little bit different. Let's actually pause here and we'll look at C and D when we come back next time. And you don't have to start any of the homework, although you're welcome to. Don't start the group work. We will do that in class next time. Have a great couple days, guys.